A fully restrained beam of length 6 meters carries a uniform load applied 2 meters from the left support to the right end with intensity of 40 kilonewtons per meter. The flexural rigidity is constant if the right support is removed. We are tasked to compute the following: the deflection and slope at the right end. And to solve this problem, you can use double integration method or area moment. And for this problem, I'll be using the double integration method to solve for the deflection and slope at the right end. So considering the right section, so we can neglect the reaction induced at the support at the fixed end. We can create our moment equation that is equal to the moment induced by this uniform load. However, it is discontinuous at this end, so we need to make this continuous by adding a uniform load both at the top and the bottom, where the load is discontinuous. And it has the same magnitude of 40 kilonewton per meter. So we have the moment induced by the uniform load at the top that is going in the same direction as m. So this is negative 40 times the distance x from the free end to get the resultant multiplied by its moment arm distance of x over 2. And then plus the moment induced by the bottom uniform load that is equal to 40 times x minus 4 times the moment arm distance of x minus 4 over 2. Simplifying, we get our moment equation that is just equal to negative 20 x squared plus 20 x minus 4 squared. And to get our slope equation, we integrate the moment equation to get negative 20 x cubed over 3 plus the integral of this expression that is 20 times x minus 4 cubed over 3 plus the arbitrary constant of c sub 1. And then integrating to get the deflection equation, we get negative 20 x raised to the 4th over 4 times 3, that's 12, plus 20 times x minus 4 raised to the 4th power over 3 times 4, that's 12, plus c sub 1 times x plus c sub 2. Now for our boundary conditions, to solve for c sub 1 and c sub 2 at x equals 6 meters, since the beam has a length of 6 meters, the deflection at this part is equal to 0, and at the slope at the fixed support at x equals 6 meters, that is equal to 0 since it is a horizontal line. So at x equals 6, the deflection is 0 and the slope is 0. So using the slope equation to get the value for c sub 1, we have 0 equal to negative 20 times 6 cubed over 3 plus 20 times 6 minus 4 cubed over 3 plus c sub 1. Now solving for c sub 1, we have c sub 1 that is equal to 1386.67, or in fraction that is 4160 over 3. And to solve for c sub 2, we will utilize the condition that is x equals 6 meters, the deflection is 0. So using the deflection equation, we have 0 equal to negative 20 times 6 raised to the 4th power over 12 plus 20 times 6 minus 4 raised to the 4th power over 12 plus c sub 1, that is 4160 over 3 times x equal to 6 plus c sub 2. Solving, we have c sub 2 equal to negative 18,000. 560 over 3. Now that we have our slope and deflection equation, we can now proceed solving for the problem. So the deflection at the right hand, that is where x equals 0, will utilize the deflection equation. So at x equals 0, we have negative 20, 0 raised to the 4th power over 12, and we cannot use this expression because this only works for values that is greater than 4. So we'll proceed with adding c sub 1, that is 4160 over 3 times x of equal to 0 minus 18,560 over 3. We get our fraction that is equal to negative 18,560 over 3, since these two expressions will yield a value of 0. So all of these expressions are divided by the flexible rigidity to get the deflection that is equal to negative 18,560 over 3 over EI. And since the value is negative, therefore the deflection of this beam is downwards. And that's all for the slope equation. We'll just set x be equal to 0, which is at the free end. So this is theta equal to negative 20 times 0 cubed over 3. And again, we cannot use this expression because it only works for x that is located between this interval, that is x is greater than 4, or between 4 and 6 meters from the free end. And then we add this up by c sub 1, that is equal to 4160 over 3. And all of this is divided by the flexural rigidity EI. And this is equal to 4160 over 3 all over EI, or basically 4160 over 3 EI. So the final answer to this problem for the deflection, that is 18,560 over 3 EI, and for the slope, that's 4160 over 3 EI. And these are our final answers.